Hello everybody and welcome to our product presentation. My name is Sönke Steenhusen. I'm from Fraunhofer Institute for Silicate Research, or in short, Fraunhofer ISC, and I will present our work on 3D printed optics. The results for innovative materials and processes for functionalized optical components were achieved together with colleagues from Fraunhofer IoT, Fraunhofer IOF and Hochschule Aachen. Quick outline of my talk. I will first present my company and will then give an introduction to 3D printed optics, so what's that all good for. Before coming to the experimental highlights, I will quickly explain the experimental background as well, and then I will conclude my talk with a question: what can Fraunhofer ISC actually do for you? Okay, this is Fraunhofer ISC in a nutshell. We are part of Fraunhofer Gesellschaft, the world's leading organization for applied research. Our main institute is located in Würzburg, in the northern part of Bavaria, which is just a 1-hour trip away from Frankfurt. We have around 400 employees dedicated to materials, processes and prototype development. And they are working on 3 locations with approximately 10,000 square meters of lab space. Our budget is around 26 million euros, stemming evenly from public funding and from industrial revenue. Our solutions can be utilized in energy, resources, biomedicine, clean environment and adaptive systems. And you can imagine that optics play a big part in all of those subjects. Okay, what is 3D printing good for? First of all, it's considered as the holy grail for optics manufacturing. So we can generate basically very complex freeform surfaces which can otherwise only be fabricated using expensive molding tools or milling technologies. The inherent freeform capability of 3D printing enables very complex and individual optical components that generate very specific light distributions for upcoming applications. But there's even more. Beyond just the mere shape of the component, we can create additional functionality, which can, for example, be in terms of optical properties. So we can integrate, for example, quantum dots for wavelength conversion. We can use grid optics, or we can introduce scattering layers. But there's also functionality on the level of electricity, so we can integrate electric circuitry for LED integration. We use 3 different core technologies in our labs. One is the printing material, an inorganic-organic hybrid polymer that we call homosur. Homosurs combine very good optical properties of glasses with the processing opportunities of conventional polymers. Moreover, but I want to explain this in detail now, we can tailor the properties of the homosur material towards the very specific needs of our customers and the processing conditions.
The second technology of relevance is more or less conventional 3D printing. I will demonstrate that we can use processes like inkjet printing and stereolithography to generate optical components. Both technologies have their pros and cons, and I cannot discuss them in detail now, but you can see a video here displaying inkjet printing process. So you can see how an optical component is fabricated in a layer-wise fashion by applying the ink and curing with UV light.
Finally, the third technology of relevance is 2-photon polymerization, or 2PP. Here we use a femtosecond laser to solidify a polymer inside the focal volume of a microscope lens. 3D scanning across the polymer and a subsequent solvent wash, we achieve true 3D microstructures, as you can see on the right-hand side of the slide.
I have compiled some optical microstructures fabricated using 2PP on this slide. So you can see that we can, for example, generate microlens arrays with freeform microlenses and also arrangements of microoptical components such as those microprisms. We can basically fabricate any microoptical component on any substrate on any desired location. In particular, we can fabricate directly on CMOS fabricated sensors. Additionally, we can generate diffractive optics with free choice of phase levels and pixel geometry. We explore the potential of 3D printing for larger optical components as well. Here you can see typical results ranging from more or less simple lenses over to freeform optics and ending in very complex optical surfaces like those LED light guides for automotive applications. One has to say definitely that those components can up to now only be used for illumination purposes. These key figures here indicate that they are not yet ready for imaging optics, but we're still working on that. Now the last part of the presentation is about the functionalization. This will only be about 2 sentences per slide, but I hope that I can give you a good impression of what is possible beyond the mere shape of the printed component. So let's start with the first function. The first function is the integration of mirrors by printing silver inks. Mirrors with a reflectivity of more than 90% can be realized inside or on printed components. The second example also relies on the printing of silver inks. Here we fabricated conductive wires to power sensors or low-power LEDs. You can see an implementation of this circuitry powering integrated signaling LEDs here. This is totally embedded inside the volume of the freeform optical component. In order to avoid stray light or ghost images, we developed different technologies to integrate optical stops or baffles into the printed component. These baffles can have random orientation inside the volume, and their transmission can be adjusted by tuning the processing parameters. We can incorporate nanoparticles such as quantum dots into the almost resin. This enables wavelength conversion from UV to visible light. On this slide you can see, for example, printed components for sensor applications which emit different wavelengths upon UV exposure. Finally, we can print scattering layers to achieve uniform light distributions, for example in interfaces or signal lights. Alright, that was the technical part of the presentation. Now is the question, how can Fraunhofer ISC help you in your applications? Well, first of all, we develop optical resins or inks based on our own source, and we can do this with respect to your specifications. Secondly, we perform process development, may it be for inkjet printing, for stereolithography, or for two-photon polymerization. And then, finally, we can utilize those materials and processes to generate freeform structures from the micron to the centimeter scale according to your designs. We enjoy conducting large R&D projects and small feasibility studies, and even some prototyping for our customers, and we are always looking for new requests, partners and customers. So with that, I'd like to thank you for your attention, and if you want to know more, follow us on our social media channels or send me an email. Thanks.